the area problem. And we barely touched on it yesterday. But the nice thing is, before we ever started chapter 12, we talked about the area problem, right? I don't know if this is going to... it doesn't. That's okay. My mouse will get it. At the very beginning, we were talking about the two big problems of calculus. And the first big problem was tangent lines. But we said, hey, secant lines, difference quotient, take a limit as the change or the separation from the tangent to the secant goes to 0. That's called a derivative. And we've talked about that in section 12.3 especially. End of 12.2, beginning of, no, all of 12.3. Yeah, all of 12.3. But then there was a second problem, the area problem. And we said this is not a geometric shape. We can't use circles or triangles or rectangles. Well, we can use rectangles if we do it this way. An approximation would be like, I don't know, maybe 4 rectangles or maybe 8 or maybe 16. But the calculus says, oh, we can keep that going. We can fit in more and more and more and more and more. And I wrote this little sigma way back when, in the very beginning of chapter 12, when you guys were still little babies of calculus. And you're still kind of, but not as bad as you were at the beginning. So let's see if we can do a little more with area than just talk about it. So here we go. Area problem. First of all, they're reviewing series and how series can be written in summations, and then reviewing a specific type of series, infinite geometric, where we were able to make this huge jump from the infinite sum of a geometric series to a limit as n goes to infinity of the S sub n formula, because this was something, the S sub n formula is something that we memorized for geometric and arithmetic. And this one, if r is in between -1 and 1, actually this r to the n will go to 0 as n goes to infinity, because basically these little fractions in between -1 to 1, the bottom wins as you raise them to powers, is one way of looking at it. And then we get left with a sub 1 over 1 minus r, a formula that we memorized. Now, we could technically do this with, before we go on to the i's and all that jazz, you don't need to write this in your notes, but we could technically do this also with a different kind of series. Guys, what's the other kind of series that we talked about besides geometric? Some of you might be wondering, and maybe you never did, but maybe you will start wondering it, why did we never do infinite arithmetic series? Why just geometric? Arithmetic, remember, that was the one where we had a sub 1, yeah, and then we had to do common differences to get to a sub 2, and then plus d to get to a sub 3, and then et cetera, et cetera, et cetera. What about quadratics, Robbie?
Like, why didn't we do that? Why didn't we skip that section this week?
Quadratics.
It's like whenever when you're trying to find the common difference, is the common difference of the differences. You know?
Oh, you're talking about the tables, the patterns. That's an algebra 2 thing. I get what you're saying, though, where like it's adding, or it's like the, wasn't it like the second difference or something is quadratics? That's kind of like being able to look at a table and figure out what type of function it is. That's kind of more stats, because stats is taking like lists of data, and we did lists, but just a little baby bit. It's not specifically stats, but it kind of is. Or experimental things like in the sciences, if you take lists of data, and then like we did with our calculator with regressions, being like, does this seem to be linear because it's going up a constant plus amount? Or does this seem to be quadratic because there's like a common second difference-ish? Or does this seem to be exponential? But we learned our calculator, there's this regression feature that kind of helps us with that. And so we never really did it by hand. But I guess like the graphing calculator handbook, the very first thing we did would have been the one time I could have probably talked about it. But yeah, Precal didn't really spend a lot of time on that. Good question, though. So common difference, plus, 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 plus. If we were trying to find the limit as n goes to infinity of that sigma, which would be, let's see, I equals 1 to n of, let's see, what's the general term of an arithmetic? Wouldn't that be a sub 1 plus n minus, ooh, I guess it wouldn't be n. I guess it'd be I minus 1. That's an arithmetic, right? A sub 1 plus n minus 1 times d, but I have to use a different letter than n because n's already being used somewhere. We could have technically said, hey, we have an S sub n formula for these arithmetic guys too. This is the A sub n formula. And then we could say limit as n goes to infinity of the S sub n formula. Let's see why we never did arithmetic. S sub n for arithmetic would end up being the first, that's the last. Remember Gauss and his little smarty pants having to add all the numbers 1 to 100? You had the first and the last, and then multiply. Oops, my bad. Multiply by n over 2. What would happen as n goes to infinity of this guy, guys? Well, yeah, we'll never get to the last term. That's one dilemma. But even if we could, like, let's say n was 10, and then n was 100, and n was 1,000. Even though we couldn't plug in a sub infinity, we could technically approach infinity, right? That's what a limit does. So how about if it's 10, and how about if it's the 100th, and the 1,000th, and the millionth? We would technically, Kyle, have an nth term for each of those separate steps. But what's happening as we add a first and a last and then multiplying by n over 2, guys? Yeah, it's still getting bigger because times a bigger and bigger and bigger n is just going to expand it, expand it, expand it. Now, it might be getting bigger positively, or it might be getting bigger negatively, but either way. Guess what's always true of arithmetic series? What's the word that describes a series whose limit is infinity? There we go. All arithmetic are divergent, so we don't even stress about them because their limits would always be infinity or negative infinity. Okay, so anyway, arithmetic and geometric, the two special series that we've talked about, but now it's time to say, there are other ones out there. And we need to talk about the other ones out there just to get an introduction to the whole area thing, the whole integration thing. So these are probably the most out there or the most important as far as you won't know them unless you memorize them. 2 and 3 and 4. The sum of I is n times n plus 1 over 2. The sum of I squared is n times n plus 1. Ooh, isn't there a pattern, just a little baby one? N times n plus 1 times, 2n plus 1. All over 6. And then I cubed is n times n plus 1, but they're both squared and over 4. Okay, so there's a baby pattern in that every single one has n times n plus 1, but then you have 2 and then 6 and then 4, and then sometimes you have squares and sometimes you don't. I'm not going into where these come from, and to be honest, off the top of my head, I don't necessarily have it the same way that I had for the arithmetic and the geometric where those formulas came from, but we're just going to assume that these are true, which they are. They're established facts. And see if we can use them to figure out, once again, what our purpose is. To figure out, basically, S sub n. Oh, you were working so well a second ago. Okay. To figure out S sub n formulas so that in taking a limit of a sigma, we can actually take a limit of a formula. That's the purpose. To take a limit of a sigma or an infinite sum, we can take a limit of a formula, which is possible. So, what if we had something like this? Just like super basic. Oh, so many lights are on. Super basic. In that question, kiddos, does or is there a formula for the summation from 1 to 200 of I? Yeah. What is it from the other page if you have, let's just keep it general first, if I equals 1 to n of I. What's this formula from the other page or from right up above for you guys? N times n plus 1 all over 2. So just showing you how the formula works. So how do we use this formula in this specific one where we have n being 200? Okay, well, as soon as we get to 200, what are we going to be plugging into the formula, guys? Who is my n? Yeah, so can't I do 200 times 201 all over 2? You guys agree? Now, you should be able to check me and see if this formula works by just doing the sigma feature in your calculator, right? But I can reduce just a little bit and make that 100. 100 adds 2 zeros, so 20100. Double check. Do you remember how to use sigma? Math? Scroll up a bit. Or isn't there alpha? window, the sigma. Throw in 1 to 200 of whatever variable you use, x or n or I or whatever's. Is it 20,100? Yeah? Go team. However, that was just using the strict formula from the page before. I wonder if they could give us anything nastier. Okay. Wait a minute. What? No, let's not go straight there. We could, but let's do one more. What if I was to ask you for the sum from I equals 1? Let's solve one more example. I equals 1 to, I don't know, something like 20. Let's not do 200. Of 4i squared plus 2. Okay. Obviously, there's no one formula from up above for you guys that fits this because it's not I alone, it's not I squared alone, it's not I cubed alone. So how are we supposed to solve this? Are there properties? Yeah, are there properties? Adam said split up, and then Kyle said something about the sixth formula. The sixth formula says if there's a constant, just bring them out and think about them later. The split up says we can do these piece by piece. Oh, so could I rewrite this guy? To be, could I pull the 4 out and do the sigma from I equals 1 to 20 of I squared plus the sigma from I equals 1 to 20 of 2? That's legal from the properties, right? Okay. Plus or minus is the property, so addition is a legal variation, right? Now, what can I use for this piece right here? Sigma from 1 to n of I squared is equal to, yeah, n times n plus 1 times 2n plus 1 all over 6. And who's my n this time? So do you guys see where I'm going to get the 20 times 21 times, what's 2n plus 1 for 20? 41. For the first piece? Gavin. Oh, check out the formula. The sigma of I squared from up above. I think it's formula 1, 2, 3. You see it? Yeah, otherwise it seems so random. Here's a dilemma though, guys. We have another piece. How are we supposed to... Is there a formula for this? I think it's number 1, right? C is a constant. So in this one, C equals 2, and here's our n, right? We already talked about our n. C equals 2, and what does the formula say about if we have a C? C by... What? Why is it so easy? Oh, if I was to ask you to solve this, wouldn't this be 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus 2 20 times? Repeated addition is multiplication, so 2 plus 2 20 times is 2 times 20. And then we could go ahead and simplify, I suppose. I mean, that's going to be a 2, that's going to be a 3. 3 and 21 is 1 and 7. 2 and 7 is 14. 14 and 2 is 28. 20 is 280. 280 times, I don't know. I'm being lazy now. 41 plus 40. Aw, too bad they didn't match. I could factor out a common 40. I guess I could still do that. Well, you know what I could do? Is anybody else thinking of this? Couldn't you do 280 times 40 plus 1? Ha-ha! Because then I could just do 4 times 280. I know, I'm just working with your mental math now. Which is going to be 2, carry the 3, which is going to be 1, 1 with 2 zeros at the end. And then there's a 280, and then there's a 40. Ha-ha! Double check my math. Because I have a 0 and then a 0. And then I have 32, carry the 3, and then 8. So then I have 11, 480, 11, 5, 20. Ha! Has anybody plugged in the sigma to see if I'm right? Adam said yeah. You can double check me though. But do you see how I split it up and then used formulas? Does that kind of make sense? If I lost anyone, I'm sorry. This one was C times N, so 2 times 20 is where I got that formula. I didn't write it out. Okay. So we have these sigma formulas. Is that table, is that yellow box, is that chart kind of important? Yes, because otherwise, how are you supposed to solve it by hand? We have these sigma formulas that say, give me a sigma and I'll give you a formula in terms of n. And if we're trying to think about infinite sums, wait, okay, hold on. We still have to think of how this applies to area. So area. How does this apply to area? So area. Area problem. Find the area between a function and the horizontal axis. Robbie, I want you to have a good grade on notes, and right now that's not going to cut it. Don't get senioritis early. I know it's hard, guys. It's the end of the year, but you got to fight for every point. And some of it's not that hard of a fight if you just pay attention in class. Find the area between a function and the horizontal axis. Now, there is supposed to be shading, but I'm sorry, it's actually really light and it's really hard to see. So let me get some shading. Let me get some shading in there. We're trying to find the area between a curve and the horizontal axis. As you guys saw from our quick little peek back at the preview of calculus, we can approximate this area by splitting the region into rectangles and adding together the areas. Now, I do have an example on the next page, but let me go ahead and, as you guys are getting this down, let me highlight, because highlighter is a little bit easier to see, a little bit easier to write on top of. It's a little bit too dark, though. Let's do something a little bit lighter. No, it's not lighter. I'm not in paint and I couldn't just fill it. That'd be way more fun. Okay. That didn't help at all. You guys couldn't even see it. Well, I saw it. Anyways, E for effort, F in success. How about this one? Can you guys see this one? No? How about this one? Can you see this one? All right. We do what we can. Yeah, the other one behind it that you couldn't see. Okay, our goal is to split this region up into rectangles and add together all the areas. Now, I'm not going to, even though I am going to show some rectangles, I'm just trying to get an idea down so you know in general what we're doing. Every single rectangle is going to be bounded somehow by the curve. So every single rectangle is going to go up and hit the curve at some sort of x. We could call that like x1 and x2 and x3 and x4. It's going to go up and hit the curve, and when it goes up, what height does it go up to? The y. That's f of x4, f of x3, f of x2, etc. We can keep on going down. So here's the idea that I want you guys to get right now, since you just wrote down area equals base times height. Do you guys see the bases of the rectangles are always going to be in between two little x's? Do you see that? The bases. It's the distance between the two little x's. So the bases I'm going to call delta x sub I. What that means is it's the delta x, the difference or the subtraction between two x's. So if it helps, you could go ahead and do something like x sub I plus 1 minus x sub I. You could do something like that. I guess we could even do x sub I minus x sub I minus 1. We could do it a couple different ways, but basically we just need to subtract two x's. We need to subtract two x's to get the base. And the heights are all going to be found by plugging in certain x's to our f value. Because remember, the f value goes up to the y's, and going up is a height, and then x values go over, and so going over is going to be a base. And once we have that idea, now we can start actually making a formula or an expression to model what we see. And that's where math gets super practical. I mean, in this section, yes, but also just in general, because if you can have some sort of situation, whether it's doing an experiment in chemistry, or whether it's modeling population growth in biology, or whether it's talking about stock growth or decay in the stock market, if you can figure out some sort of mathematical expression to model it, then maybe you can predict what's going to happen, or you can express what's going on in between, or you can find some sort of pattern. Math is used in all sorts of places, but let's go ahead and see if we can take this idea of taking an area, splitting it into rectangles, and modeling in some way, shape, or form the area that we're supposed to find. So I'm going to zoom in on this graph so you guys can see it. I just wanted to make sure that you guys got down bases are delta x's and heights are f of x's. Bases are how far in between x values, and heights are going up to the curve or up to the function, up to the y's. So now we have something specific. Now we have an actual function, 6 minus x squared. It's a parabola, whoop, facing down. We have the x-axis that's bounding it or stopping it on this side. We have the parabola on this side, and then we have the lines x equals 0 and x equals 2. And what they want us to do is use 5 rectangles. They're telling us exactly how many to use to approximate the area of the region bounded by. There's a few different ways of doing this, but I'll show you what way makes sense in my mind first. And then I'll show you the shortcut to writing it out. What makes sense in my mind says, hey, let's find each of the rectangles. We'll find the first and the second and the third and the fourth and the fifth. And every single rectangle is going to have some sort of base times height. You guys agree? Rectangles, bases, heights. Okay. What do you notice as you look over here at these rectangles, first of all, about their bases? What would you just, like off top of your head, looking at this 0 to 2, what would you think the base is as far as a distance? Yeah, 2/5. How did Tony get 2/5? You see it? You're going from 0 to 2, and there's a distance of 2 in between that, right? So my delta x, or my base, is going to be, well, how far in between? Well, that's 2. And then what are we splitting it into? 5s. So if I was to go 5/5, let's check it. That'd be 2/5, because that's too small for me to write. 4/5, 6/5, 8/5. If everything works out well, 8/5. Where should I end or land? 10/5. Yep, which is 2. Does that make sense? Okay. So I could actually, for every single one of my rectangles, couldn't I say that each of them have a base of 2/5? That part's easy. Each of them have a base of 2/5. And if we're taking some sort of region, whether it was from 1 to 10 or 3 to 70 or 2 to 5, whatever region or space we're taking, if we're splitting it into 5 rectangles or 10 rectangles or 8 rectangles, we can do that process of what's the distance in between the x's and how many pieces are we splitting it up into. Now, those are bases, but what else do we need? Heights. Can you guys take your first rectangle? Can we just, I don't know, the first one is the one on the far left. Does that sound good? If we were to take the first rectangle, how high does he go? F of what x, though? Do you see where he hits the curve? Does he hit the curve at 0? Is it 6? No. He hits the curve at, who's that guy? 2/5. Oh, he hits the curve at 2/5. So it'd be, now do we know that off top of our heads? No. Somewhere between 5 and 6. But what could we use our calculator to do? Plug it in, and we could do 6 minus 2/5 squared. 2/5 squared would be 4/25, and 6 minus 4/25. Well, 6 quarters would be 150 cents, right? So 6 quarters, 150, 25ths minus 6/25, so 144 25ths. But we could use our calculator, right? Or we could use fractions. But I'm not so much worried that you can do all that mental math in your head. I'm just worried, do you guys get that we had to go over to 2/5 then up to make that rectangle? Okay, so what about the next rectangle? Who's he going to use as the x to go get the f? 4/5. Do you guys see a pattern? Who's going to be next? 6/5. Are you using my number line yet? The next one's going to be 8/5. And everything works right. This guy should be hitting at 2. Do I have little baby expressions for how to find the area of the first, second, third, fourth, and fifth rectangles in this picture? Yes. But what am I supposed to be doing? Using all 5 to approximate the area. Now, let me be really snazzy for just a second, okay? The actual area, the shaded that you guys can't even see because it's so light, is behind it. The perfect little part of the parabola would actually be written mathematically as the integral from 0 to 2 of the function 6 minus x squared dx. Whew, that's really precise. That's like the snazzy way of writing it. There's actually something in your calculator that might be able to do it. But that's the actual area. But what do you see right here? Approximately, because are we doing the actual area if we add together these 5 rectangles? No. But what are we doing? Well, finding a good guess. Could I write out all of this here? Yeah. But what do you guys see is common for all of them? 2/5. So maybe instead of writing it all out, maybe I'm just going to write the f of 2/5 plus f of 4/5 plus f of 6/5 plus f of 8/5. Come back. I'll be back. You guys can continue my pattern. You don't need me, right? Wasn't it f of 8/5 next? F of 8/5 plus f of 10/5, which is 2, right? Those are all the heights, but what do I need to multiply all those heights by? Okay. Wait a minute. Do you see all this repeated addition going on? Huh. Is there some sort of mathematical operation or Greek letter that does like a repeated addition over and over and over again? Ooh. Could I go sigma from I equals 1 to 5, 1 to 5, of f of, could I do something like 2/5 n times 2/5? Now, yeah, Kyle's totally right. I have an I, n is my top guy. I guess I should do I. Is that going to do what I want it to do? 2/5, and then 4/5, and then if I plug in 3, 6/5, 4, 5 would be 10/5. Times, Can you guys plug sigma in? Now I'm going to do it 2 ways in my calculator because some of you guys, I already know, are like, my calculator doesn't have it, or I don't have my calculator on me. Well, I guess you couldn't do anything in your calculator then. But, oh, my calculator's in the AP exam because somebody forgot it. Can I borrow someone's calculator? Don't ask me. I'm not sure they had it all year, which is the scarier part. Actually, 2 people forgot them. Okay, one way is that you could go to your math, and you could go get your sigma, and we already talked about there's a shortcut for this too, but you could go get your sigma, summation, and go from, I'm just going to do x as 1 because it's easier than going and finding the I. There are 5 rectangles. It's going to be f of, wait a minute, f of, maybe I should have put my f over here in my y1 because my calculator can do this, right? 6 minus x squared is my y1. And then can't I go get a, alpha trace? Guys, remember that your calculator can do function notation? I can do 2/5 times x. If you don't like that, you could have done 2/5 times x, if you like it that way better. And then don't I still need the other bases, so 2/5? Boop. Uh-oh, it doesn't like it. Oh, I had too many parentheses. 6 minus x squared, I think. Double check me, guys. Is it 6 minus x squared? I put 2/5 outside the little guy. There we go, 2/5. Boop. I got 8.48. Anybody else? which would be the same thing as if I was to do this the long way of 2/5 plus y1 of 4/5 plus y1 of 6/5 plus y1 of 8/5 plus y1 of, how long do I keep doing this till?
Until you get there.
Oh, good, until I get to the end. And then I have to do my 2/5, right? All my bases. Whoo! I got it. Did you get it? 8.48. Y1 was your function, which was 6 minus x squared. And I got that from the problem because the problem said f of x. So f of is y1 of. So either way, we end up with our 8.48. There you go, Vika. Thank you, thank you. And our 8.48 to what? To approximating with 5 rectangles. What would have changed if I had had 10 rectangles instead? You would have divided by 10, and you would have had 10 of these. Or you would have gone from 1 to 10 of that. Oh, that's not too hard. But what's the question if they want the actual area? Uh-oh. The actual area, I would have had to have an infinite amount of those, right, guys? And the problem is, if I had an infinite amount of those, I actually would have needed to make some sort of formula. I'm going to write that formula here that some of you might want to peek at, because that formula is exactly what you would need to use in order to find the infinite sum, or the actual area. And that's what we're going to have to finish off with tomorrow. You guys have quite a bit to start on homework tonight. See you guys later. B minus A all over N. Nope.
14.25. That's what's in the book. I don't know how.
A plus B minus A all
I'll figure it out.
times I. There you go.
How do you do the y1 in the calculator?
Oh, the shortcut way is the alpha button, how you do fractions, but do alpha trace instead.
No, like how to actually.
Oh, your graph.
Yeah. Oh wait, maybe because I put 20 for n for a second.
Yeah, just get it back to me, kiddo.
y1. Yeah. It's just in
What's the? Still try 5
yeah. Like this? No. This is
Yes. What does it look like? Oh, you did what I did. The 2/5 needs to go inside the summations because it needs to be for every single piece. Because that guy ends the sum. Yeah, get rid of your times. Got him.
oh.
Yeah.
Oh, I just looked at the graph. I didn't use a formula.
Yeah, I think you can do quite a bit. Just the sigmas and then the 5 rectangles. Just saying it says actual area or going to infinity.
Yeah, it was thinking you started.
Yeah. So, like, because I didn't know how to do the formula yet until today.
There you go.
Plugging.
That one didn't work.
Yeah.
Which formula? This one?
Uh.
Oh, what's that?
Oh, that's the infinite one. That's what we're seeing tomorrow. Never mind.